All right. Well, welcome. This week we're going to be talking about choosing the correct statistical test. So what we're going to do is we're going to review type 1 and type 2 error definitions. I'm going to talk about what's meant by power, statistical significance, clinical significance, and confidence intervals. Review different types of data, and then we'll spend a majority of the lecture discussing how to choose a statistical test. All right, so to go back and review, previously we talked about random sampling or probability sampling and randomization or random assignment. Remember, random sampling is when you're sampling subjects randomly from a population of interest. Random assignment is where you're randomizing, or say like a flip of a coin, of subjects to a treatment or to a control group. So if you have a random sample and you have random assignment, then we can make causal inferences, meaning cause and effect, to the whole population, okay? Whereas if you have a random sample but no random assignment, you cannot make any causal inferences. You can only examine relationships or associations, but you can still generalize to the whole population. Now, if you have no random sample, but random assignment, you can only make causal inferences to that sample. And an investigator would need to, if they're trying to draw conclusions to the general population, that can be difficult. But sometimes they will try and justify and say that the sample is, based on the characteristics, is representative of the larger population. But in general, without true random sampling, it can sometimes be difficult to truly draw conclusions to a generalized to a population. Now, if you have no random assignment and no random sample, you can make no causal inference, and you can only examine correlations for that sample. So I hope this helps. Other concepts that we've talked about before are confounding variables. So you can have extraneous variables, which are factors that are other than the independent variable that may affect the dependent variable. And a confounding variable does not affect the dependent variable, and it confuses the effects between the variables that are under study. So say, for example, you have a study that you're looking at the effect of vitamins on the impact on myocardial infarction. And maybe you do a case control study where you've gone back in time and identified patients who had an MI and who did not have an MI, and you look at whether or not they had taken some vitamins. And maybe you find a difference, or maybe you don't. But maybe it's not necessarily that the vitamins were what caused the outcome, but some other confounding variable. Maybe gender also has a relationship with maybe how somebody may or may not take vitamins. Maybe more women are more likely to take vitamins than men. I'm just making an example. And likewise, maybe men are more likely to have a myocardial infarction. So that could be gender in that case could be considered a confounding variable. All right, let's talk about type 1 and type 2 errors and some general issues surrounding sample sizes. Okay, so type 1 error is the error of rejecting a null hypothesis when it is actually true, or what this is a false positive. It occurs when we're observing a difference when in fact there really is no difference. For example, you wrongly find somebody guilty of murder when they're truly innocent. When we're thinking of type 1 errors, a term that's commonly referred to this is the alpha. And you can see the Greek symbol I've listed there, which is the probability of rejecting the null hypothesis, given it is true. And typically we set that at a probability of 5% or 0.05, meaning 5% of the time we're willing to identify differences that are really, in fact, due to chance. Now, a type 2 error is accepting a null hypothesis when, in fact, it is false. It's a false negative. And this typically has to do with sample size or the power of a study to find a difference. So this is failing to observe a difference when, in truth, there really is one. And this is a common problem in a lot of medical research, and certainly even in anesthesia studies, that, especially if they don't use do a power analysis or get a good estimate of a potential, what we call an effect size. So this is where you do not convict a person of murder when in fact they really did commit the murder. And so that would be a type 2 error. And so a term that goes along with type 2 error is power. And this is the ability to find a difference or an association or a relationship when one actually exists. And it's typically set at 80% of the time. And another term that goes with this is the beta, which is the chance of making a type 2 error, which is typically set at 20%, meaning 20% of the time we're willing to take the chance of making a type 2 error. So you can see we're much more conservative with type 1 errors because we don't want to convict somebody of murder when they're innocent. So that's why you have a p-value of 0.05, but we're a little more willing to accept that we won't find a difference when in fact there really is one, and we're willing to take that 20% risk. Other key terms that you need to be aware of is an effect size. So this is the extent to which a difference or relationship exists between variables in a population. Sorry. Now, when we do a power analysis is how we calculate our estimated sample size that we'll need for a study. And so what goes along with that is we need to determine effect size, which we'll talk about in later lectures, which is essentially the magnitude of the effect that you're looking for. We need to set the alpha level, and we need to set the power of the study. So a type 1 error you can see here would be versus a type 2. A type 1 saying you're pregnant when in fact you're not, and the opposite being a false negative saying you're not pregnant and in fact she really is. So they're good analogies. The p-value, which I've already mentioned, it's called that level of significance. And we've already discussed, it is the probability that we'll make a type 1 error. And the p-value is typically can be influenced by the sample size. So larger studies tend to find clinically irrelevant findings, and small studies can find non-significant findings when in fact they are clinically important. Now, what's the difference between a one-tailed and a two-tailed p-value? You're going to read this when you're searching the literature. So remember back, the null hypothesis is that two populations are really the same, and the observed difference between the samples is merely due to chance. So when we said a two-tailed p-value, what we're saying is we're not making any prediction about the direction of the relationship or the difference at the outset. So this is something that an investigator needs to decide on prior to executing their study. A one-tailed p-value, you must predict which groups will have the larger mean before collecting any data. The big difference is that when you do a one-tailed p-value, the p-value is about half that of a two-tailed p-value, which means you tend to have a little bit, you can get away with maybe a little bit smaller sample size and still find significant differences. So here's an example. You're conducting an experiment on a new antibiotic that impairs renal function. And we're looking at the creatinine level as our outcome measure of renal function. So a two-tailed p-value tests the null hypothesis that the drug does not alter the creatinine level, which is our dependent variable. A one-tailed p-value tests the null hypothesis that the drug does not increase the creatinine level. So what you're saying here is with a one-tailed, sometimes that's referred to as a directional we're already at the outset saying the direction we feel that we're going to find. So prior to our data collection, you would propose to use a one-tailed p-value if you're confident based on a review of the literature that that new antibiotic would not impair renal function. All right. What are confidence intervals? Confidence intervals it really refers to it's the precision of the results of a study. And so typically we have what's called a 95% confidence interval. So maybe you have a mean value, and we have a 95% of confidence interval, which means that you're going to have 95% of the time the value that you find is going to fall within that population within that range of values. So say, for example, you have a 95% confidence interval of 27 to 51. And that means that if you repeat that same clinical trial 100 times, you can be sure that that result will fall within that range. So wider intervals indicate a much lower precision, whereas narrow ranges have much greater precision. And typically when we're thinking of precision of the confidence interval, when you have larger sample sizes, you tend to see much narrower confidence intervals. And in power, just as we go back to it, this is the power of a statistical test, is the probability that the test will reject the false null hypothesis. So as power increases, the chances of a type 2 error decrease. And I've already touched on these earlier, but I think it's nice to reinforce the concept. So the statistical criterion that we use is the p-value. The effect size is the size of the difference or the magnitude or strength of the relationship. And also, power also depends on the sensitivity of the data. So if we use very highly reliable instruments, that helps improve the power of our study. Or we have additional controls through a rigorous research design, as well as power is also largely dependent on sample size. So larger sample size studies have a little bit more power to find or detect differences. Now, statistical significance refers to how likely the differences or relationships are found are real and not due to chance. Now, clinical significance is how large the difference or strength of the relationship is. And so really what we're looking, we can find things that are statistically significant, but they're clinically irrelevant. And so a lot of times when we're looking at clinical relevance, we're also looking at measures of effect size, relative risk, or odds ratio, which we'll talk about in later lectures. And it really helps answer the question, is the difference or relationship between the groups or outcomes large enough to be worth achieving? And as I said, studies or findings can be statistically significant, but clinically irrelevant. So here's an example. A large clinical trial of a new antihypertensive agent finds on average it decreases mean arterial blood pressure by 1 millimeter when compared to conventional therapy. And you can see the p-value was there at 0.03. So is that clinically significant? Well, I would make the argument that, in fact, no, it is not. A 1 millimeter difference is not clinically significant. So that is that sometimes the challenge when you have very large sample sizes, we can find differences when, in fact, they don't really mean anything to us.